Why do bridges collapse from buckling? Imagine walking across a bridge and suddenly feeling it sway or crack beneath your feet. What causes a structure to fail so suddenly and dramatically? One major reason is buckling, a failure mode that can lead to catastrophic collapse. Buckling happens when parts of a bridge, especially those under compression, deform out of shape and lose their ability to support loads. It's like a tall, slender pole bending under too much pressure, but in a bridge, it can happen to beams, girders, or cables. This failure occurs when the load on a structural element exceeds a certain critical point, called the buckling threshold. When this happens, instead of just compressing, the element bends or twists sideways. The longer and thinner a component is, the more prone it is to buckling because it can bend more easily under pressure. Think of a thin straw bending when you squeeze it. That's similar to what happens inside a bridge when certain parts are too slender or not properly supported. Design flaws play a big role in buckling failures. If a bridge's beams or supports are too narrow or lack enough bracing, they can buckle under stress. For example, during construction, if a key component gets bent or damaged, it can weaken the entire structure. Over time, corrosion and rust can also weaken metal parts, making them more likely to buckle when loads increase. Imagine a rusted metal beam that suddenly gives way under the weight of a heavy truck. Temperature changes add to the risk too. When materials expand in heat, they can become weaker and more prone to buckling. If a bridge deck expands unevenly, it can cause cracking and deformation, which might lead to buckling in critical parts. Excessive or uneven loads, like overloaded trucks or strong winds, can push parts of the bridge beyond their buckling limit. The Tacoma Narrows Bridge, for instance, collapsed because wind caused twisting and torsional buckling, which the design couldn't handle. Support conditions matter as well. If the foundation shifts or settles, it can change how forces are distributed across the bridge. This can increase stress in certain members, making them buckle unexpectedly. When engineers study failures, they see that many collapses happen because of a combination of these factors: poor design, deterioration, environmental effects, and unexpected loads. To prevent buckling, engineers focus on making parts stiffer and better supported. They use stronger materials and design members with wider cross-sections to resist sideways deformation. Regular inspections are vital to catch early signs of corrosion or deformation. If a support shifts or a member starts to bend, fixing it early can save the entire bridge. Considering thermal effects and dynamic forces like wind during the design process also helps avoid buckling failures. Understanding why bridges fail from buckling shows us how fragile structures can be when multiple factors come into play. It highlights the importance of careful design, maintenance, and constant monitoring to keep bridges safe. When engineers recognize early signs of buckling, they can take action before a small problem turns into a big disaster.